Okay, so now in this video we'll talk about the uncertainty principle for position and momentum for a free particle in a line. Okay, so let's see. So what we have is we're given some particle on a line, and it's in some superposition, and we measure it. So we could measure its position. And in general, of course, its position is not going to be fixed. Remember, the outcome of a measurement always gives us it's probabilistic. So when we measure the position, we might discover that this is x versus the probability of x, and it could be that we have some probability distribution which might look like that, and there's the expected value of x. So maybe the expected value of x in this case might be 0, and then there's our measure of uncertainty delta x, which is just the variance of our probability distribution. So this is just the expected value of x squared minus the expected value of x, whole thing squared. Okay, that's the square of the standard deviation. So this is sigma squared, and which is a measure of how spread out this distribution is. But now we could also measure its momentum. And when we measure its momentum, we are measuring P and probability that we actually see the momentum P, little p. And again, we get we might get some sort of a probability distribution which might look somewhat different than this. And again, we are interested in the spread in P, which is the expected value of P squared minus the expected value of P, whole thing squared. So it's the square of the standard deviation of this curve. And what the uncertainty principle tells us is that delta x times delta p must be greater than or equal to h bar over 2. So that you can try to make the position as definite as possible, but then you lose complete control over the momentum. Or you could make the momentum as definite as possible, and then you lose complete control over the position. Or you could try to make both of them somewhat definite, and then you saturate this bound, and no matter what you do, you cannot squeeze the position and the momentum simultaneously down to being completely definite. Okay, so now let's try to understand intuitively where this uncertainty principle comes from and what it tells us about momentum, etc. Okay, so in the first video, I remember I said, well, we can't really talk about velocity because how do we measure it? But now, since we are speaking informally, I'll even talk about velocity, and we'll see how we get sort of a position, velocity, uncertainty principle. Even though we cannot really measure velocity, but we can still talk about it. So here's our picture. So our picture is, we have some superposition. Let's say it looks like this. This is psi of x comma t. And then after some small amount of time, let's say the superposition sort of, it starts looking more like this. So this is psi of x t plus delta t for some delta t. So now, if I tell you that this, okay, so if I tell you that this was the superposition at time t and this was the superposition at t plus delta t, these are not quantities that you could measure. Remember, if you actually measure the particle, if you measure the position of the particle, you just see it in some position x with probability which is proportional to psi xt squared, magnitude squared. So this is the wave function. The wave function is not accessible to you when you do a measurement. But I'm willing to give it to you. I'm willing to tell you that the particle had wave function psi of xt at time t, and it had wave function exactly psi of xt plus delta t at t plus delta t. I'll give you their functional form. I'll tell you everything about it. And now I ask you the question, what is the velocity of the particle at time t? Okay. So let's see how you would answer this question. Okay, so suppose that you did a measurement of this particle at time t, and you asked, what is the chance that I'll find the particle at point x? Well, remember, this is a continuous function. It's like continuous probability distributions, right? The chance of finding it at x is 0. So you really want to ask, what's the chance that I find it in a tiny interval around x and x plus delta x, right? And the answer is, the chance is exactly it's the integral from x to x plus delta x of psi of x t magnitude squared dx. So it's an integral. It's this integral of the square of the amplitude over this interval. Okay, so you know, if the amplitudes are real, you can eyeball this probability as being the area under the curve. Okay, so now, given that you know what's the chance of finding the particle at any given point along this, in the black curve and in the blue curve, which direction is this particle moving in? Well, on the one hand, you know, if you look on this left-hand side, it looks like the curve is sort of moving out towards the left, because your chance of seeing the particle in this region is higher in the blue curve than in the black curve. In the black curve, you're more likely to be in the middle here. So it looks like you're moving left. But symmetrically, if you look on this side, the chance of being in the blue curve is higher. So it looks like you're moving from the middle to the right as well. So which one is it? Is the particle moving towards the left, or is it moving towards the right? Well, the answer is, the particle is in a superposition of velocities. So it's moving left at a certain velocity with some amplitude. It's moving left with a higher velocity with some other amplitude. It's moving right with a certain velocity with some amplitude. So it's just like this superposition we had in position, where you could ask, what's the position of the particle? And the answer is not that it's in a particular position x, but it's in a superposition over all real values, over all real locations along this line, each one with some amplitude. And so it's the same way with velocities. It's in a superposition of all possible velocities, all possible real numbers which describe the velocity of this particle. So now, can we make this more quantitative? Can we understand this in a somewhat better way? So here's a way to understand it. So you see, if we were still talking about the position of the particle, we could say, what is that wave function where the position is completely determined, where it's not a superposition, but it's actually completely determined? Well, it's a delta function. So if you want to know, if you want to say the particle happens to be at the point x, then the wave function would be 0 everywhere else, but then it would be a delta function at x. So the integral, the square of the integral of the square of the amplitude would be 1 at this, in this small interval around x. So it would be this delta function, which is so that it's a normalized function. It's the square of psi x squared would be 1. Okay, so what about velocity? So what would the wave function look like which has a definite velocity? So let's start guessing. So let's look at psi of x, which is of the form e to the I kx. So it's a complex exponential. So what do I mean by this? So it looks like this. So here's the real line, and now I'm again looking at a cross section at this point, and what I want to say is, so this cross section sort of, here's the real, this is the complex plane, that's the imaginary axis, and so our amplitude of psi of x, so psi of x at this point is a point in this plane, and since psi x is of the form e to the I kx, so it's somewhere on the unit circle, so it lies somewhere on this unit circle, and maybe it's at this point. Okay, but e to the I kx sort of precesses as so this point precesses as you go along as x changes. And so one way to draw this function, where if you imagine it looks sort of like a slinky. So where this distance, which is a period of this, is 2 pi over k, right? Because after 2 pi k over units, if x goes from x to x plus 2 pi, so what I'm saying is psi of x equal to psi of x plus 2 pi over k, because e to the 2 pi I is just 1. Okay, so now let's say that we start with this as our, so let's say that this was psi of x t equal to 0. So this is at time t equal to 0. And now we want to understand what psi of x is as a function of t. So I claim that psi of xt is going to look like something like e to the I kx plus omega t. Okay, so basically what's going to happen is that this complex exponential is just going to precess in time. So it's if you imagine this complex exponential, it looks like a slinky, one of these metallic slinkies. And if you've ever played with a slinky, what's happening when you evolve this in time, when you evolve psi x in time, I'm claiming, is that it starts rotating at a certain rate. The slinky starts rotating at a certain rate, and so it starts rotating. And if you've ever played with a slinky and if you've seen what happens when you rotate it, well, it seems to translate at a certain rate. It seems to move at a certain rate. Okay, so what we are going to claim is that this is the kind of wave function, even though it's unnormalized, but this is the kind of wave function which has a definite velocity. So now to work out its velocity, we just apply Schrodinger's equation. So I d psi by dt equal to d squared psi by dx squared. I'm still using the rough form of Schrodinger's equation without any constants, because we are not doing anything very precisely today. So if you substitute this in here, what you get I d psi by dt. Well, what you get I times, what's d psi by dt? It's I omega e to the I kx plus omega t is equal to d squared psi by dx squared. So what's d squared psi by dx squared? You'd get I k squared e to the I kx plus omega t. Right, so what you have is that omega equal to k squared. So what this tells us is that psi of xt equal to e to the ik x plus kt.